Now we're going to do an example of flow through a surface to show you how to use that surface integral. And we are given the scenario below. We have this rectangular duct that is 2 meters wide and is 0.5 meters high. And this duct is very long in the x direction, and it has water flowing through it, and it has a uniform velocity of 3 meters per second in the x direction. So you could say that v is equal to 3 meters per second I hat. And the problem is asking us to find the mass flow rate and v dot through the following arbitrary surface. So here we just have a planar surface right here that is inclined at an angle of theta with respect to the y-axis. Okay, so it's just a straight planar surface, and we are asked to find m dot and the volumetric flow rate through that surface. So first, as always, we need to use make some assumptions. So here there aren't very many. So assumptions. Again, always write these down. 1, we'll assume uniform flow, which is kind of given to us. And 2, we'll assume constant properties. Okay, and then since we're asking for, since we're given numbers, we will first derive the formula in terms of letters. Then we will stick in the properties to find the numbers. So we'll just look up the properties. We need m dot, so you can think we're going to need the density of water. So we will write that down. And we know that rho of H2O equals 1,000 kilograms per cubic meter, and that's in the appendix of the textbook. Okay, so now we have listed the assumptions that we can invoke, and as you work on more complex problems, it's always a good idea to leave some space for additional assumptions, because as you work through a problem, you may realize that you need to invoke additional assumptions in order to solve it. Okay, so now we are ready for the solution. And note the angle theta. We are not given an explicit value for the angle theta. Okay, so as I said, we will find an expression for m dot in terms of rho, h, w, theta, and v. Okay. So essentially, our surface here, I'm just going to do a two-dimensional cross-section of it, because you've seen that my 3D drawing skills are definitely not the best. So we have a height here h, and it's of width w. Okay, and we have the surface here. Again, it's a 3D planar surface, so it extends into the page, but my drawing skills are not up to snuff, so I will not do that. And we have an angle theta between them, and now we know that v is traveling in the I hat direction, so we have v equals some v I hat, and we have n hat pointing down and away from the surface. Okay? And to find, and I'll draw XYZ again. And to find m dot, we need the surface integral of rho v dot n hat dA and the volumetric flow rate is equal to the surface integral of v dot n hat dA. Okay, so on the surface, we need essentially v dot n hat all along that surface and the density all along that surface. So first, let's find v dot n hat. Okay, so we'll just draw a little velocity vector here for v. V equals v I hat. And we have the surface here. And this angle theta, this here will be angle theta. And n hat will point in this direction. And you can just use properties of trig, and n hat will equal to cosine theta I hat minus sine theta j hat. Okay, so we now know n hat. Again, it just points normal to the surface, like that. And so because we know the angle with respect to the y-axis, we can then figure out what n hat is in terms of theta. Then v dot n hat equals v I hat, because that's what v is, dotted with cosine theta I hat minus sine theta j hat. And you can do the dot product and you wind up with v cosine theta. Okay. And note, this is not a function of x, y, z, or really it's not a function of the position along the surface, because theta is equal to constant and v is uniform. Okay, and that implies that n hat is constant, and if both v and n hat are constant, then essentially v dot n hat will also be constant. Okay, so we know v dot n hat. So now we are almost ready to go to the integrals, and I'll go to them. So m dot will equal the area integral of rho v dot n hat dA. Well, we're assuming constant properties, so we can pull out the density. And by our uniform flow assumption, we can pull out v dot n hat, and we have rho v dot n hat times the surface integral of dA, and by definition, that is just the area. So then this implies that m dot equals rho, and I'm going to substitute in our result for v dot n hat, and that's rho v cosine theta times the area. Okay, then v dot equals the integral over the area of v dot n hat dA, and again that's constant, so that equals v dot n hat times the surface integral of dA, which again is just the area. So this implies that the volumetric flow rate is just equal to v cosine theta times the area of our surface. Okay, so now we need to find the area of the surface. So we know v dot n hat need to find A. Okay, and to do that, let's look at the geometry of the channel and our plane. So we have this height here is h, and the surface makes an angle theta with respect to the horizontal, and then it's perfectly planar. Oops. And it has width W. So it's a planar surface. So this area is, we'll call this side here L. A equals L times W. Now what is L? So we can find L by just looking at the triangle here. We have H, theta, and there's L. Okay, and so you can use properties of trig, and you can find that L equals H over cosine theta. So that implies that the area of our plane is just equal to HW over cosine theta. Okay? So now we can find that m dot equals rho v cosine theta times the height of the channel times the width of the channel over cosine theta. Notice that the theta dependence goes away. We get the same m dot no matter what angle we choose. So this implies that m dot equals rho times the x component of the velocity times hw. Then similarly, the volumetric flow rate equals rho v cosine theta times the area, which is hw over cosine theta. Again, the theta dependence disappears, and this implies that the volumetric flow rate is equal to v hw. Okay, and note, because rho is constant, m dot is just equal to the density times the volumetric flow rate. Okay, but we can only do that because the density is the same on this portion of our planar surface as it is on this portion of the planar surface. If the density is different here than it is over here, then this does not hold. Okay. So I can't stress that enough, and it's for dealing with eventualities like that in your guys' career that I expect you, when you are working these out, I expect you to start from the basic definitions and basically work through everything in a disciplined, methodical manner that will avoid mistakes. And then that way, if you need to use these principles in your career for a much more complicated scenario, you know that you maybe can't go from here to here, and so you know you need to find a way to evaluate that directly. Okay, but now we are ready to stick in the numbers. Okay, m dot equals rho v h w. That equals 1,000 kilograms per cubic meter. Notice I put the units right after the number. Times 3 meters per second times 0.5 meters times 2 meters. And notice that all the meters cancel out, and I'm left with m dot equals 3,000 kilograms per second. And notice I showed all the unit cancellations right with the numbers here. In fact, I was even picky enough to where the exact order that I put in the numbers matched the exact order of the symbols in the formula. That was an additional requirement on homework when I was a student, is that the grader was instructed to give us a 0 if we didn't do this. I'm not that picky, but it may seem a little bit over the top. But down the road, when you guys need to study, putting the numbers in the exact order that they are listed in the formula basically actually helps you study down the road after you've sort of forgotten some of these principles, and you need to refresh your memory. That way you know exactly what number corresponds to what variable. Okay, and then v dot equals our formula that we derived, VHW, that equals 3 meters per second times 0.5 meters times 2 meters. And that implies that the volumetric flow rate is equal to 3 cubic meters per second.